Hi, welcome to series of webinars on optical network technologies and protocols. This is Brahmanan GS. The main objectives of this series of webinars is to discuss about SDS SONET, Ethernet packet over SDS SONET, WDM, OTN Ethernet packet over OTN WDM, element management layer and network management layer functionalities in reference to optical networks, project management in optical networks development and testing environment. So apart from these series of webinars, if we find any topics more interesting and more relevant, we will keep adding them as and when it's required. First, we'll discuss about SDH SONET. The topics for this series of webinars is to discuss about the history of SDH SONET. Basically, the history of SDH SONET lies in PDH. We'll discuss on building blocks, layered architecture and frame structure, synchronization in SDH SONET, protection mechanisms, fault management, performance management, discussion on very specific network elements of leading telecom manufacturers with their features. We shall also discuss about a couple of protocols which are being used for communication between a layer which manages the network elements and the network element itself. We shall have to discuss the functionalities of element management layer and network management layer. And then we'll take up some of the scenarios and specific applications wherein SDH SONET is more relevant. Ethernet packet over SDH SONET. So this will be high-level topics of our discussions as part of series of webinars on SDH SONET. So let's begin. As we discussed, the history of SDH SONET lies in PDH. PDH stands for Plesiochronous distal hierarchy. The word Plesio means close, chronos means time. It means that close time. It's a Greek word. It means almost synchronous but not completely synchronous. So PDH is a technology for transporting voice or data between multiple devices which are working with clock sources with accepted tolerance levels for synchronization. It means that if I have a network, two network elements which have to be communicated between each other, then these two network elements work on different clock source, not necessarily aligned to a primary reference clock. Primary reference clock is more precision clock whose specifications are described in ITUT G811. If you are interested in knowing the complete details of the PRC, you can refer to this particular standard. So PDH is almost synchronous but not completely synchronous. So it's a digital transmission hierarchy. And pulse code modulation is the technique which is used in PDH networks, which is based on time division multiplexing. See, PCM, pulse code modulation, is the basis for almost all the digital hierarchies which came from PDH onwards. So the main mode of PDH data was through twisted pair, coaxial cable and microwave. In order to discuss about a series of digital communication networks or optical networks, in order we need to understand PCM first. What is PCM? PCM means we get some pulses, we code them and we modulate them. So there are three stages in pulse code modulation: sampling, quantization and encoding. We know that voice frequency varies from 300 Hz to 3.4 kilohertz. So it's approximately 4 kilohertz. If at all we need to convert any analog signal into digital signal and get transported over any media, these signals have to undergo sampling, quantization and encoding. What is sampling? Sampling is a process wherein I convert an analog signal into different pulses. So, but it has to be sampled at some rate. So, sampling frequency is equal to or greater than or equal to 2 times voice frequency. It means that it should be almost equivalent to 8 kilohertz. This is based on the great scientist Nyquist. It means that any analog signal can be sampled and digitized only if it is sampled 8,000 times per second. So it means that we get 8,000 samples per second. So the output of sampler looks like this. So there will be, if this is x-axis is time and y-axis is amplitude, we get 8,000 such samples per second. Quantization is a process wherein every sampled amplitude pulse is given a relative number. So there are different quantization mechanisms. There are quantization mechanisms whereas the levels from 0 to 255. It means there are around 256 smallest levels possible. So we also know that log 2 of 256 is equal to 8. So in order to represent every sample, the quantized relative value can be represented with 8 bits, right? So we need 8 bits, and finally it will undergo an encoding. So there are different encoding mechanisms, so output of which gives us 8 bits per sample. So as we have 8,000 samples per second, so 8,000 into 8, which is equal to 64,000. So it means that every voice signal can be converted into digital signal, and the output of that digital signal would be equivalent to 64,000 kilobits per second. This is what I call it as DS0. So 64 kbps digital data is called as DS0. This is the foundation for any discussion that we are going to have it in the future. So, and DS0 is a voice digital form of the voice signal. If at all I need to transmit that data over hundreds of kilometers, I cannot lay separate twisted pair or coaxial cable for that one particular voice channel. So a mechanism wherein I can group multiple such channels is called as multiplexing, right? So there are different types of multiplexing. So one of such multiplexing is time division multiplexing. There are different standards being used, adopted across the globe. T1 is a standard which was adopted in North America, and even is a standard which is adopted in Europe and Asian countries. So once we multiplex DS0, we will have to get DS1. So it could be, a standard based on T1, or it could be standard based on E1. If we multiplex such 24 DS0 channels, this is called as PCM24. So T1 is based on PCM24. 24 is because we have 24 channels. Now this has to be transmitted within 125 microseconds, because 1 divided by 8000, we have 8000 frames per second. So 1 divided by 8000 is equal to 125 microseconds. Similarly, in E1 there are 32 such channels which are named from 0 to 31. But the time slot 0 is used for frame synchronization, and time slot 16 is used for signaling channel in E1. Now, so the data rate of T1 is equivalent to 1.544 megabits per second, right? And similarly, E1 is 2.048 megabits per second. So just because there is a fundamental difference between the base DS1 standard adopted by North America and the rest of the world, especially Europe and Asia, the hierarchy of these two standards also varied. So this is an hierarchy for North American standard, which is based on T1. So as we seen in the last slide, T1 mux multiplexes 24 voice or data channels and gives us the output of DS1, which is equal to 1.544 megabits per second. Similarly, if you multiplex 4 such DS1s, we get DS2, whose data rate is 6.312, and similarly we get, multiplexing such 7, we get, DS3, and multiplexing such DS3s by the factor of 6, we get DS4. We notice one thing very clearly here, that 4 times DS1 is not equal to this particular rate. 4 times 1.44 megabits per second is not equivalent to 6.312. Right? So the difference is occupied by justification stuffing bits. So what are these justification stuffing bits? See, as these two devices work on different clock sources with some variation, maybe the variation of 50 parts per million, even with that variation over the distance, over time, these datas reach the input data rate varies. So they come at different intervals of time, of course, but the thing is, when the mux expect some data, there may not be data. So what this mux does is, it inserts some justification bits to compensate the speed, and it ensures that output data rate is fixed. So this continues. So the overhead gets added at all the stages. We also notice one thing, that this is bit interleaved multiplexing. It means that this mux takes one bit at a time at each and every channel to get the output. So when the data rate increases, the efficiency of these muxes decreases, because they got to handle in bit by bit and the data rate keep increasing. Right? But one of the smallest advantages of this bit interleaved multiplexing is, just because it interleaves by bit, the buffer or a memory which is required for this particular muxes can be small. So because it need to process only small data at a given point in time, right? So this is what is hierarchy of T carrier. And similarly, in E carrier in Europe, the same thing happens. We get 2 Mbps, the output of PCM30 mux is 2.048 megabits per second. So if it is given to 2:8 mux, the output is 8 Mbps. The same given to 8:34 max, it gives out 34 Mbps max. So by the factor of 4, these get multiplexed. We'll have to notice one thing very clearly, that at every stage the stuffing bits are added in both T carrier hierarchy and E carrier hierarchy. We have to measure one thing very clearly, that when the data rate increases, the overhead percentage also increases. So stuffing bits which we add gets increases when the data rate increases. So this is one of the biggest drawback of PDH. Okay, so now let's quickly compare between the T carrier, E carrier and J carrier. So North America, we call it as T carrier, Europe E carrier, Japan J carrier. We notice quickly that the only similarity between all the three is at DS0. And when we compare between T carrier and E carrier, there is no similarity in any stage of muxing. So basically there are 4 levels of muxing. There is no similarity. Of course, there are some similarities at DS2 level between T and J carrier, between North America and Japan. But in distal mux level 4, there is no similarity. It means that there is no similarity between these two standards of T carrier hierarchy and E carrier hierarchy between North America and Europe. But still, there were some provisions made in the PDH hierarchy to have an interoperability between these two carriers. So we have DS0, we have this is DS1. So E1 is 2.048 Mbps. So in order to get 6.312 megabits per second, which is DS2 or T2 of E carrier, we need to multiplex by 3. And similarly, in order to get E4 of E carrier, we have to multiplex by the quantum of by 3 to get E4 from DS3 of T carrier. So some changes were made to have an interoperability. But we have to mind one thing, even during this interoperability as well, there is a huge stuffing get added, right? Okay, so let's take one a quick E carrier hierarchy. So E1 has got 32 frames as we discussed, which is equivalent to 256 bits. And similarly, E2 will have 848, E3 will have 1536, and E4 will have 2928. So we notice that within 125 microseconds, that means that the frame size increases, but the frame duration remains the same. So let's discuss about even frame structure and what and all the provisions available within the frame structure for synchronization and transmission management and signaling. So there are 32 time slots. Time slot 0 is a this particular time slot 0 is basically used for synchronization and transmission management. Typically, this particular bit 1 in this time slot 0 is always set to 1. We consider this bit as, international bit. But there are certain cases wherein we use these bits for cyclic redundancy check, which we'll discuss in the next slide. In the time slot 0, from bit number 2 to bit number 8, this is what is called as frame alignment signal. If you notice that this is common 00111011, this is a standard word which indicates the frame alignment signal. Whenever this particular data is being received by a receiver, the receiver understands that, okay, so it is the beginning of the new frame, right? So this frame alignment signal exists in time slot 0. And please make a note that this frame alignment signal exists in the alternative frames. So how many frames we'll have? We'll have 8,000 frames. So every alternative frame will have frame alignment signal. If you note that, so this is frame is called as FAS, frame alignment signal frame. This frame is called as non-frame alignment signal. Non-frame alignment signal, first bit is always 1. Normally this will be 1. And bit 2 is also 1 to avoid simulation of the frame alignment signal. Suppose frame alignment signal starts with 0. If this is not 1, and if for some reason if this also becomes 0 and the rest of the other bits also become 0, the receiver will consider this as in beginning of new frame, right? So which is wrong. So in order to ensure and to avoid the simulation of the frame alignment signal, the second frame, that is non-frame alignment signal frame, bit number 2 is always set to 1. And the third bit is a bit in the non-frame alignment signal, which is used for remote alarm indication. So if there is any alarms between a transmitter and a receiver or vice versa, suppose if there is a loss of signal or a loss of frame or out of frame, this information is transmitted in the bit number 3 in the non-frame alignment signal frame. And rest 5 bits in the non-frame alignment signal are spare bits, and they are used for national use. I mean, this could be used for many purposes. This could be used for point-to-point applications, could be used for exchanging the status messaging of synchronization between transmitter and receiver. Mind that if these bits are not used, they are set to 1. Okay, now we discussed the first bit in the time slot 0 is a national bit which can be used for many purposes. One of the biggest use of this particular bit number 1 in time slot 0 is for cyclic redundancy check. So what is cyclic redundancy check? Cyclic redundancy check is a process which is adapted to protect the simulation of frame alignment signal. That's number one. And the second one is it induces error monitoring capabilities within the frame structure. Say for example, I have a transmitter, I have a receiver. If these two devices are getting, data exchange, they are exchanging the data, what I do is, once a frame is built in the transmitter, I use a cyclic redundancy check. It means that I will do some multiplication, division, whatever is the remainder, I will put it in these cyclic redundancy 4 bits which are there in the bit number 1 of time slot 0. So C1, C2, C3, C4. So these are all the bits which have the data which get transmitted within the frame, within the next frame in fact. Once this data is received by the receiver will also use the same method of cyclic redundancy check. It will calculate the CRC of the data received, and it will have its own cyclic redundancy check mechanism, so through which it will compare between the information which is transmitted over these cyclic redundancy bits and what is the reminder that it gets after analyzing the frame received from this. So if there is any difference between those reminders, then it flags off an alarm saying that there is a bit error which are getting transmitted in these bits, right? So these bits carry error information when CRC4 is established. So this gives a better protection mechanism for my data. So we need to clearly understand that when we implement or when we configure CRC4, this works at 16 frames. These 16 frames are considered as one multi-frame, and these 8 frames are considered as sub-multi-frame. So the logic of CRC is exchanged for every 8 frames. So when an error is received, we will understand that it is for the previous sub-multi-frame. So frame alignment signal frames are used for cyclic redundancy checks, and mind that these alternative frames are used for multi-frame alignment signal. So when CRC4 is implemented, this will have 0 0 1 0 1 1. So this indicates that this is the beginning of, or this indicates that we are within a particular multi-frame, right? So for CRC4, errors are monitored in the bit A, whereas for the multi-frame, the errors are monitored through bit E. That is the difference. So this is a brief explanation about time slot 0. So time slot 1 is basically for signaling information. So whenever have a word in the bit number 1 of time slot 16, 0 0 0 0, this will indicate that it is multi-frame alignment signal, right? So this indicates that it is the beginning of multi-frame. So this is being used as a multi-frame alignment signal, which indicates that it is the beginning of a channel associated signal time slot. So what is this channel associated signaling? So as we know, we have 30 channels within DS1 or E1. So every channel will have its own communication channels or signaling channel. So this is for channel number 1, 2 to up till 15, and this is from 16 to 30. So every channel will have almost equivalent to 2 kbps line. So every channel is associated with a 2 kbps channel through which a lot of information exchange between a transmitter and receiver for a specific channel. This is a channel specific signaling, right? So establishing of the call, engage of the call, phone number exchanges, destination phone number, source phone number. And so this will give an intended signaling information between a caller and called party. Okay, and bit number 6 is used for alarm within channel associated signaling environment. If there is any alarm, this A bit is being used, and there could be loss of signal, loss of multi-frame alignment. So those errors, informations get transmitted in the bit A, right? And if suppose sometimes they don't use this bits B, C, D, then if at all they don't use, then this will be set to 1. Sometimes some for some specific point-to-point communication, we don't need all the 4 bits for each channel, during which time we use only 1 bit. Okay, so this is a brief information about channel associated signaling. Okay, this is an high-level view of PDH, and if you are very interested to know more about PDH, I suggest you read following recommendation from ITUT G703, which talks about physical electrical characteristics of the interfaces, and then G704, which talks about frame structures of all the rates supported in PDH. G705 talks about the equipment functional blocks, and if you are very fond of knowing CRC4, you can refer to G706, and all the pulse code modulation related recommendations. A lot of information is being shared in G series from G731 to G755. You can refer to this. And G806, it talks in general about the transport equipment, description of methodologies and generic functionalities of transport equipment. This is quite generic document which talks not just PDH, it talks about SDH, it talks about OT and WDM, everything. So this is generic document which you can still refer it. Okay, so now let's quickly discuss about what PDH offered and what were the limitations. See, we know that when we discussed, we said that somehow we can, because of the framing byte or a framing byte somehow we can find the start of the beginning of the frame. But it is very difficult to know the beginning of the tributaries when it. Say for example, I have a 140 Mbps link running. I can know the beginning of 140 Mbps frame, but within which, if my 2 Mbps signal is being transmitted, I cannot know the beginning of that frame unless and until I demultiplex 140 Mbps to 34 Mbps to 8 Mbps to 2 Mbps. I would not know where is my tributary. So this is the biggest drawback of PDH. So the major limitations of PDH are, PDH networks were using multiplexers which were bit interleaved. It means that it is to take bit by bit from the input data and give the output. So processing of the bit by bit data at the higher data rate is very challenging, and it induces a lot of delay as well. And the next is lack of flexibility. Taking out a specific tributaries from a very higher data rate is very costly affair, as we need to demultiplex the higher order data rates in reverse order of their multiplexing. So we just discussed in one of the slides that in order to demultiplex and get 2 Mbps out of 140 Mbps, we used to use bank of multiplexing multiplexers to get the 2 Mbps. And one more important thing is, even if we take 2 Mbps out of 140 Mbps by series of demultiplexing, if at all the rest of the data is intended for any other location, we have to remultiplex every time we demultiplex. This indicates that there was no flexibility within PDH networks. Lack of consensus on standards. So beyond DS4, DS5, there were no standards. Every manufacturer used to use different design techniques. They were using different coding techniques, decoding techniques. Interoperability was very challenging, and the standards were defined for electrical interfaces, but they were not defined for optical interfaces. So we know that electrical data cannot increase indefinitely. The only solution is changing over to optical interface. So lack of consensus on standards was the biggest challenge as part of PDH. OM was really nightmare because there were only limited number of bits being used as part of the frame structure, which we have seen it, and resolving the issues and frequent call drops, quality of service issues were humongous in PDH networks. And these networks were basically used for point-to-point communication, and they were not used for ring architecture. And self-healing ring absence itself is the biggest limitation of PDH. And there were no much of bits or bytes in the frame structure for network management functions. There were signaling channels, but network management channels were missing from the frame structures of PDH. And no PRC, no primary reference clocks for all the network elements, because there was a drift in the clocking sources. There was huge jitter issues, which leads to data corruption as well. So no PRC was a biggest challenge for PDH. And we know main mode of transmission was through coaxial cable and electrical interfaces and microwave. We know that these medias induces electrical interferences. So that being the case, there was a lot of signal attenuation which demanded for more repeaters in the network. And nowadays, we are all bandwidth hungry people. We need more bandwidth for voice, data, video streaming, IPTV, and many more applications. See, the best data rate which worked in PDH was 140 Mbps. I mean, if a particular family wants 100 Mbps or beyond that, and the maximum data rate supported by PDH is 140 Mbps, how can we think of having having PDH network installed at every home locations, which is not possible. So that's the reason why PDH networks are getting uh, superseded by SDH, SONET networks, and OT and WDM networks. So most of the disadvantages that we discussed in PDH can be overcome by SDH SONET. So which we will going to discuss from our next webinar onwards. Thanks for watching. If you liked my webinar, please subscribe to my channel, and if you have any comments, please do write your comments. And thanks for watching. Thanks a lot.